Hi, everybody. It's Professor Mitchell, and we are finishing up Chapter 5 today, looking at Section 5.6 on further counting techniques. In this section, we will look at problems with tossing coins, problems about roots, and problems about balls drawn from an urn. And I've even thrown in a few extra problems at the end, a couple which I'm saving for audience participation. All right, so we'll start with tossing coins. An experiment consists of tossing a coin 10 times and observing the sequence of heads and tails. So we're going to use the methods of this chapter to figure out first how many different outcomes are possible, total. How many different outcomes have exactly 2 heads? How many different outcomes have at most 2 heads? And how many different outcomes have at least 2 heads? I forget how many of these there are. Okay. How many different outcomes have exactly 4 heads with no 2 heads consecutive? So these get kind of fancy after a little while. All right, so we'll start with the first question. So here is one possible outcome. H stands for heads and T stands for tails. Since each coin has 2 possible outcomes, by the generalized multiplication principle, the total number of possible outcomes is 2 times 2 times 2, a total of 10 times, which is 2 to the 10th, which comes out to 1024. And that's because you have 2 choices for the first flip, 2 choices for the second flip, 2 choices for the third flip, and so on. So one important thing about this, and this may help you when you're doing your problems, it is pretty common for one of these counting problems to come in several parts, like this one did, where the very first part asks you how many total outcomes there are. So if you ever notice that, just keep in mind that automatically means the answers to all of the later questions, right? How many outcomes have exactly 2 heads, at most 2 heads, at least 2 heads? All of those outcomes have to be less than 1024, right? Because this is the grand total. So just keep that in mind. All right, for letter B, here is one possible outcome with 2 heads. In this particular case, the 2 heads came up first and third. So those 2 heads must be placed in 2 of the 10 possible positions. So the number of outcomes with exactly 2 heads is 10 choose 2, which comes out to 45. Now, it might seem it might not be obvious to you, why are we using a combination here rather than a permutation? And the reason is, if you look at this particular outcome where the heads were in the first and third positions, having the heads in the first and third positions is exactly the same thing as having them in the third and first positions. So the ordering of those positions does not matter. Okay. All right. For letter C, at most 2 heads means there can be 0 heads or 1 head or 2 heads. So what we have to do in this case is count the number of outcomes with 0 heads, count the number of outcomes with 1 head, count the number of outcomes with 2 heads, which we've already done, and then add those numbers together. There's only one possible outcome with no heads, and that's if all 10 coins are tails. So there's only one like that. There are 10 choose 1 or 10 possible outcomes with 1 head, which also makes sense, right? The 1 head could be first or second or third or fourth, etc. So there are a total of 10 of those. By the way, I want to point out that if you did 10 choose 0, for this first one, 10 choose 0 does come out to 1. So that does work. And then we already figured out there are 10 choose 2 or 45 possible outcomes with 2 heads. So the total number of outcomes with at most 2 heads is 1 plus 10 plus 45, which is 56. All right, next, at least 2 heads. Well, on the one hand means 2 heads or 3 heads or 4 heads or 5 or 6 or 7 or 8 or 9 or 10. All right, but I really don't want to do it that way because that's going to take a long time to figure out all of those. Easier way to do it is to note that at least 2 heads means that there are not 0 heads or 1 head. So we already know that there's 1 outcome with no heads. There's 10 outcomes with 1 head. So there are 11 possible outcomes with 0 or 1 head. Those are the outcomes that we don't want. And then remember from letter A, there are 1,024 possible outcomes total, which means that the number of outcomes with at least 2 heads is all of these except for these 11. So we're going to do 1,024 minus 11, which gives you 1,013. All right, whoops, I just realized that I hadn't noticed earlier that the solution to letter E was not in my PowerPoint. So I had to take a moment just now and add that in. So let's have a look at that. Okay, so this is counting the number of outcomes that have exactly 4 heads with no 2 heads consecutive. And I will admit to you that this is a pretty difficult problem. I'd say on a scale from 1 to 10, this is about a 9 as far as counting problems goes. The thing about counting problems is that they are often pretty difficult, but as you do more and more problems, you start to kind of develop a bag of tricks that you can, then use your experience with previous problems to solve new problems. So in this problem, each outcome is a string of letters containing 4 H's and 6 T's. We are asked to count the number of such outcomes in which 2 H's are never adjacent to each other. One way to construct such an outcome is to write down 6 T's, the way that I've done below, and then decide where to insert the 4 H's. The arrows below, which you'll see in just a second, show the 7 places that the H's can be inserted. So you can put an H right at the beginning, you can put an H right at the end, or you can put an H between any 2 letter T's, but only one, right? Because you're not allowed to have 2 H's next to each other. Those 4 insertion points can be selected in 7 choose 4, which comes out to 35 ways. Therefore, there are 35 outcomes without consecutive H's. And now we can move along to this problem. A tourist in a city wants to walk from point A to point B, as shown in the maps below. What is the total number of routes with no backtracking from A to B? So just notice, let's look at these examples. In this example, the tourist walked 2 blocks south, and then 3 blocks east, and then 1 block south, 1 block east. So we could represent that route by writing S-S-E-E-E-S-E. Or in this route goes E-S-E-S-E-E-S. Okay. So a little bit of a similarity with the last problem, right? Instead of strings of H's and T's, now we're looking at strings of S's and E's. All right, so if S is walking a block south and E is walking a block east, the 2 possible routes shown in the maps, already talked about this. So all routes can be designated as a string of 7 letters because no matter which route the tourist takes, it's always 7 blocks. 3 of which will be S and 4 of which will be E. Selecting a root is the same as selecting where in the string the 3 S's will be placed. Therefore, the total number of possible roots from A to B is 7, choose 3, which comes out to 35. And I'll tell you a fun story about a year or two ago. The Stockton escape room, I think it was running a promotion on Facebook where every day they put up a little brain teaser and they were giving free tickets to, I don't know, the first 10 people who commented with the answer. And one day they had a problem just like this. It was a little grid and it asked how many roots are there from point A to point B. So I knew how to do this problem. And so I commented with the answer and I won tickets to the Stockton escape room, which I'm sad to say I never used. But anyway, there it is. All right. That brings us to selecting balls from an urn. An urn contains 25 numbered balls, of which 15 are red and 10 are white. A sample of 5 balls is to be selected. First question, how many different samples are possible? Total, right? Letter B, how many different samples contain all red balls? And then finally, how many samples contain 3 red balls and 2 white balls? All right, so for letter A, a sample is just an unordered selection of 5 balls out of 25. So the number of ways to make that selection is 25, choose 5, which comes out to 53,130. So remember, just like in the flipping a coin 10 times problem, this is going to be the cap on all of the other answers in this problem, right? Because all of the other questions are specific ways of selecting 5 balls. For example, in letter B, they want to know how many ways are there to make a sample of only red balls. In that case, we would select 5 balls out of the 15 red, which is 15, choose 5. That comes out to 3,003. And then finally, this is a really useful problem. This trick is going to come up again and again. To form the sample with 3 red balls and 2 white balls, we must first select 3 red balls from the 15 red balls, and then select 2 white balls from the 10 white balls. Using the multiplication principle, this gives you 15, choose 3, times 10, choose 2, which comes out to 20,475. All right, so now we're going to look at just a couple of additional examples I threw in here. I am going to do 2 of these for you, and then I'm going to leave the other 2 as audience participation problems that you could try to do in the discussion if you are a student in my class. So I'm going to do examples 1 and 3. Example 1 is how many poker hands, and for those of you that are unfamiliar with poker, I will tell you everything you need to know, consist of 2 cards of one rank, 2 cards of another different rank, and 1 card of a third rank. This kind of poker hand is called 2 pairs. And then skipping down to number 3, how many 9-letter words? I think I've mentioned to you once before that in finite math, when we talk about a word, we're just talking about a string of letters. It does not have to be a real word. How many 9-letter words with no repeated letters contain the 5 vowels in alphabetical order? So one example of a word like that is the word facetious. All right, so I'm going to show you those 2 problems, and then I'm going to leave number 2 and number 4 for audience participation. All right, so for number 1, how many poker hands consist of 2 cards of one rank, 2 cards of another different rank, and 1 card of a third rank? That's called 2 pairs. So let me give you the background that you need. Recall that a standard deck of cards has 52 cards. sorted into 4 suits, which are clubs, diamonds, hearts, and spades. And each suit has 13 ranks, which are the numbers 2 through 10, and also Jack, Queen, King, and Ace. And then a poker hand is 5 of these cards in any order. Okay, so I apologize. There's no easy way to animate the rows in a table, so just try to look at it one row at a time. The way I like to do these problems is to use the multiplication principle and then organize it into steps. So the first question I could ask is, which 3 ranks are in this hand? There's going to be 3 different ranks, right? Because, for example, your two pairs might be 3 of hearts, 3 of diamonds, 8 of hearts, 8 of clubs, and queen of diamonds. Okay, just as an example. So the first selection that needs to be made is which 3 ranks are in the hand. In this example, the 3 are 3, 8, and queen. And the order does not matter for those. And then the next thing I need to decide is which 2 of those ranks are the pairs. All right, so this is not the example I just said. In the one I just rattled off, there were 2 3s and 2 8s. Okay. So in this example, let's say it's 3 of hearts, 3 of diamonds, 8 of clubs, queen of hearts, and queen of spades, for example. There are 3 choose 2 ways to choose 2 out of the 3 ranks to be the paired cards. Then you have to choose the suits for the low pair. And by the way, nothing special about the low pair. I'm just specifying that it's one of them. There are 4 choose 2 ways to make that selection, for example, hearts and clubs. And then I have to do the same thing for the high pair, for example, hearts and spades. And then I have to choose the heart for the single card. You could write that as 4 choose 1, but it just comes out to 4. So then using the multiplication principle, actually they call it the generalized multiplication principle. The number of different 2 pair hands is 13 choose 3 times 3 choose 2 times 4 choose 2 times 4 choose 2 times 4, which comes out to, and you should try this on your calculator, which comes out to 123,552. There are, just FYI, about 2.6 million different possible poker hands total. So the ones with 2 pairs account for maybe about 4% of those, 4 to 5% of those. All right. So now let's go to example 3. How many 9-letter words with no repeated letters contain the 5 vowels in alphabetical order? For example, the word facetious. So the first thing to do is to choose the other 4 letters in the word. All 4 of those letters would have to be consonants, because remember, this word is going to have all 5 vowels in it. And since it said there were no repeated letters, that means the other 4 letters all have to be consonants. So in the example of facetious, the other 4 letters are C, F, S, and T. And for now, those could be in any order. But then I have to choose 4 spots in the 9-letter word to place those letters in order. And actually, give me just a second here. I'm going to make something a little clearer here. Okay, I decided to create some space here so that it's clear that these are spots for 5 different letters. Okay, so the second step, after I've chosen which 4 consonants are going to be in the word, I have to choose 4 spots to place those letters in order. In the example of facetious, we're putting an F in the first space, a C in the third space, a T in the 5th space, and an S in the 9th space. putting those letters in any other order would create a different word. So not only do you have to choose the spots 1, 3, 5, and 9, but you have to assign them to specific letters. So that means that order does matter when you make that selection. And so the number of ways to make that selection is P of 9, 4. And since it said that the vowels are in alphabetical order, that means that the vowels are automatically going to go, A is going to go here, E is going to go there, and then I, O, U. So we are actually done with the steps. Once you make this selection, everything else just automatically falls into place. And so by the multiplication principle, the number of different 9-letter words with no repeated letters containing the 5 vowels in alphabetical order is 21 choose 4 times P of 9, 4, which comes out to a whopping 18,098,640. And that's going to do it for section 5.6. That's going to do it for chapter 5. We will see you next time.